Hey everyone, thanks for tuning in again. In today's lab, we'll be going over a refresher to ANOVA. So specifically what we'll be looking at are two types of procedures for making mean comparisons. The first one is what I'll call DIY contrast or do-it-yourself contrast, and the second is Tukey's HSD or honest significant difference procedure. So for DIY contrast, we'll look at one complex and one pairwise. So complex comparisons are where you aggregate means across a combination of groups and compare that to another combination of groups or one group. So the main point there with complex comparisons is that we're aggregating groups or combining groups together and making comparisons between combinations. And then there are also pairwise comparisons, which are just between two groups at one time. So in this example, we'll be testing a single contrast at a time. So hypothetically, the scenario is that we've decided on a comparison we'd like to make before running an analysis. So this is also called a planned comparison. And in these situations, it's not really necessary to run the Omnibus Anova, but sometimes software will give it to you anyway. But it's just important to note that when you're running a planned comparison analysis, you do not need to run the Omnibus Anova, and you can just focus on the comparison that you're interested in. For more than one planned comparison, the process is a bit more complicated and there are more things to consider. So typically it's a common requirement that contrasts are orthogonal or independent, and that the maximum number of contrasts that you're allowed to test, and this is for maintaining a type 1 error rate of alpha equals 0.05, so the maximum number is equal to the number of groups minus 1. So for instance, if you have a factor with 3 levels or 3 groups, then you're allowed to test 2 contrasts, or you're allowed to make 2 mean comparisons. So the distinction between planned and post hoc comparisons or contrasts can get lost because contrast can be used either before or after. It's the choice of the researcher whether they want to do it before or after, but the distinction is still very important for controlling type 1 error. So having planned contrast is always recommended. The second thing we'll be looking at after DIY contrast is Tukey's HSD procedure. This is a post hoc procedure, so we do it after running our Omnibus Anova, and if we find the Omnibus Anova f-test to be significant, then we can make all pairwise comparisons while maintaining alpha equals 0.05 using Tukey's HSD procedure. So the data that we'll be working with, I'll post it online. It's called anovadata.dat. For SPSS users, it'll be anovadata.sav. So we have a grouping variable, which is a categorical variable. It's called group, and there's 4 groups. There's the control group, the treatment group, treatment 1 group, treatment 2 group, and treatment 3 group. So there's 1 control group and 3 treatment groups, giving us 4 groups total. And then we have Y, which is a continuous outcome. So with that, let's go ahead and get into the lab. Alright, so here I have SAS open, and the file that I've opened, which is available online, is ANOVA lab _template SAS. And so what we'll do first is we will read in our data set, and I'll do that using a point and click method. So I'll go to File, Import Data. Just give it a second here. And so I want to import a tab delimited file. I put all of the data sets on my C drive. So here's my C drive in the datasets folder. Remember that it's limiting everything to .txt, so I have to change that to all files. And then here we have the ANOVA data .dat. Go ahead and open that. Click Next. I'd like to call the dataset ANOVA data, and then I can go ahead and just finish. Alright, so 100 rows were created, and we have 100 observations for 2 variables. That sounds right. If we go into libraries in the work folder, we can take a look at our data. And so we have group variable, again, which is a categorical variable specifying whether a participant is in the control group, which is group 1, and then either treatment 1, treatment 2, and treatment 3, which corresponds to group 2, group 3, or group 4. We can see that here as we scroll down. And then we have Y, which is our continuous outcome. So that looks good. I'll go ahead and exit out. First thing I'll run here is I'll set my output delivery system to HTML. And then remember these lines here, starting at save until the end, and then ODS RTF path. That and these two lines here, ODS RTF close and quit, we'll save those until the end. And so if you'd like to output, or if you'd like to export all of your SAS output from this lab into a Word document, all you have to do at the end is uncomment this line here, the ODS RTF path, and then uncomment these two lines here, ODS RTF close and quit. And then if you rerun all of the syntax with those three lines uncommented, your output will be exported to a Word document. All right, so what we'll do first is we'll compute our group means. So I'll use proc means. My data set is called ANOVA data, and again I want the mean. I'm going to do it by class, so I'll use the class statement, and so my grouping variable is called group, and then the variable that I'm interested in, which I'll put in the var statement, is y. And then I'll just go ahead and run that. And then we get our group means here. So for the control group, which is group 1, it's about 24. For group 2, which is treatment 1, it's about 30. For treatment 2, which is group 3, about 28. And then group 4, which is treatment 3, about 31 here. All right, going back to the syntax, we'll go ahead and run our first DIY contrast, which is a complex comparison. So my planned comparison, I want to test whether the control group is significantly different from the combination of all of the treatment groups. So to test that, we'll use proc GLM. Our data set again is ANOVA data. In the class statement, again, our grouping variable is group. Our model is we want to look at y and how that differs across each group. So y is equal to group. And then we can go ahead and set our contrast here. So I'm going to give it a name, so control versus all treatment groups. And then for the group variable, I'd like to set the contrast -3, 1, 1, 1. So remember that the switch in signs here is indicating that I'm comparing this single column to the combination of these three columns, since these three columns all add up to 3. The change in sign from negative to positive means that that is where we are making our comparison. And then remember that column 1 is group 1, and then column 2 is treatment 1, column 3 is treatment 2, and column 4 is treatment 3. So again, this one group, which is -3, compared to the combination of all of the treatment groups, our 3 treatment groups. So +1, +1, and +1, which adds up to +3. And then we can go ahead and run this. So we'll scroll up here. Here's the beginning of our output. And so here's our contrast. We can ignore all of this stuff here. We don't need it. All we're interested in is in the contrast that we have specified. So if we look at the F value and the P value, which is less than 0.05, we answer our question and can say that the control group is significantly different from the combination of all of the treatment groups. And that's it. So that's the first contrast. All right. Moving on to the second contrast that we'll specify, my planned comparison is the control group versus treatment 1. And so I'm going to ignore treatment 2 and treatment 3. And so I'm only going to be comparing the means from control and treatment 1. So this is a pairwise comparison. So to run this, I will use the procglm again, and then same data set. All right. Class is group. The model stays the same. And then here is where we make our change. So the title of my contrast this time will be control versus treatment 1. And again, I will change my group contrast to -1, 1, and then turn off group 3 and 4, which are treatment 2 and treatment 3, the groups that I do not care about. 0 and 0. So again, we want to compare column 1 to column 2. And so I specify -1 for the column corresponding to the control group, and then +1 for the column corresponding to treatment 1. And then I turn off treatment 2 and treatment 3. And go ahead and run this line or this model. We scroll up a little bit. Okay. So again, this can all be ignored. All I care about is this here, control versus treatment 1. And again, here's our F value, and then our P value is less than 0.05. So this answers our second question, which is the control group is significantly different from treatment 1. All right. So that was our second DIY contrast. So now we'll move on to Tukey's HSD procedure. All right, so here we do care about the Omnibus Anova, so we'll look at that in our output. And then given that our Omnibus Anova is significant, which means that the groups are significantly different from each other, we could take a closer look and see which groups differ from which other groups. So for this, we will use a procglm once again. Our data set is the ANOVA data set. Again, a lot of this will remain unchanged. Class, in the class statement, we want to use group because that's our grouping variable. The model does not change. Okay. Here, we use the mean statement instead of contrast. And so group is our grouping variable, so that's what we're interested in. And then alpha, we want to specify that we want to maintain a 0.05 alpha level. And the procedure that we will use is Tukey. And then we can go ahead and run our model. Okay, so if we scroll up, this is our Omnibus Anova. So our F value is 10.46. It's significant. So there is a significant difference among the groups. And so I will follow up with a post hoc 2-key test. And here are the results. So the means covered by the same bar are not significantly different. So looking at this, what we can tell is group 1, which is our control group, is significantly different because it is this red separate bar from the blue bar. So our control group is significantly different from treatment 1, which is group 2, treatment 2, which is group 3, and treatment 3, which is group 4. Alright, so in other words, the control group is significantly different from each of the treatment groups. So control versus treatment 1, significantly different. Control versus treatment 2, significantly different. And control versus treatment 3, significantly different. Okay, so all of the pairwise comparisons. But each of the treatment groups is not significantly different from each other because they are covered by the same bar. So so group 2 is not significantly different from group 3. Group 3 is not significantly different from group 4, and group 4 is not significantly different from group 2. So a little weird because I'm used to getting each comparison on its own separate line with its own separate p-value, but here we have a little bit of a visual representation which nicely summarizes the significant differences here. Alright, so we started with our DIY contrast where we set the contrast ourselves, and then our first contrast was a complex comparison looking at one group versus the combination of 3 groups, and then we ran our own pairwise comparison looking at the control group versus treatment 1. We also looked at 2-keys HSD procedure where we ran our Omnibus Anova. Given that that was significant, we followed up with a post hoc 2-key test, which showed that the control group was significantly different from all of the treatment groups, from each of the treatment groups, but the treatment groups were not significantly different from each other. And with that concludes this lab, which was an ANOVA refresher in SAS.